So this morning you will hear from Professor David Flynn about how he and his team will work on symbiotic systems for resilient autonomous robot missions. David's going to present his work for about 20 minutes before we will open for a few questions at the end. Please post your questions throughout the chat or in the chat throughout the presentation, and we will address as many as we can at the end. Any that we don't get to, we will take a note of and we will follow up afterwards and send a response to everybody. So just before I pass over to David, I just want to talk about what happens after today. So as we've had the 5 events this week, where hopefully you've had be able to get a good understanding about the work that we'll be carrying out in the ORCA Hub extension. We will then be hosting a series of what's called AIM days in the first 2 weeks of August. So there'll be one AIM day for each of the challenges that we've set ourselves. The purpose of these AIM days is to give you an opportunity to speak one-to-one with the academics leading the work.
Well, good morning and welcome everyone. I'm going to introduce you to this program of work where we are seeking your engagement to inform this demonstrator in terms of its design and objectives. And to support you in engaging in this work, I'm going to give you a summary of what symbiotic systems is, how we have tackled some of the challenges around resilience in autonomy to date, as well as safety compliance, just so you get an understanding for the foundations of which we're building on. And then I'm going to give you an insight to how we have designed this new work so far. So, symbiotic systems, okay, we know throughout a multitude of applications, we have critical infrastructure, which are going to require us to operate, maintain and design them in an increasingly challenging environment and markets. We've got significant investments in offshore wind, significant investments in nuclear, but many other areas of critical infrastructure. So the vision, how can we address the operational challenges? So this is taking a top-down view of how we create trustworthy autonomous assistance, okay? So not a ground-up perspective, we're looking at what are the operational barriers or bottlenecks to us using trustworthy autonomous assistance. So how can we deliver the resilience that's required, the productivity, and of course, the safety compliance, okay? How do we achieve this with an optimal partnership with human in the loop, appreciating that the world is dynamic and needs will change, okay? So I want to give you, obviously, our view. What's the lens we've applied to this challenge, okay? So there are a multitude. So just very briefly, because I appreciate we've got a lot of people from industry, you know the issues, you're working at the sharp edge of industry. On the right-hand side there, you're seeing how things are done today. These offshore infrastructure, whether it's renewables or oil and gas, already has a lot of intrinsic monitoring embedded within it. Condition monitoring systems, structural health monitoring systems. These can be prone to error and fault. It's very data rich, okay? And if we look to, instead of treating autonomous systems as the one-size-fits-all solution, what about we apply the perspective of it is one element within a cyber-physical system? Can we create a hyper-enabled capability where the robot is coordinating, collaborating, cooperating with the resident monitoring systems, okay? So this leads me into the proposition that we're offering stakeholders and partners who engage with us is we want to give you, as part of this work, a cyber-physical architecture that transfers to your use cases, okay? We're going to demonstrate it for you and verify it for you in this program of work, which concludes in end of March next year, okay? But the enabler, the kind of enticement we want to give you is you can take this cyber physical architecture we have designed, built and verified and tune it to your operational needs, your robotic platform requirements. Why? Well, it's to fast track how you can do reliability, safety, compliance and resilience. I appreciate that these robotic platforms will just represent a risk and a cost burden until we remove those barriers, okay? So what are we building on to date? What have we done? And I'm going to provide this presentation. Of course, it's being recorded, but I'm going to provide you with the links to these videos, which I'm sharing with you, which really set the foundations of how we've designed this work moving forward. So just very briefly, and I'm going to be highly selective in the material I show you. So firstly, thanks to the hard work of the team, point one on your screen, we took existing information and knowledge, some online data that was available, and we coupled it with a clear, addressable need of using autonomous underwater vehicles with low frequency sonar to inspect subsea power lines. Now, what that gave us was an ability to actually provide advanced asset management and planning capability on that particular use case. Okay, we took the knowledge of the engineering team, because data and robots are not a substitute for knowledge, they're an enabler of that knowledge. So we created one of the world's first subsea cable asset management system coupled with robotic assistance. Okay, and what did that lead to? We could forecast fault type and location within about a month of failure accuracy. Now, that met the design criteria for that challenge. It needed to be accurate within 2 to 3 months, given the nature of operations in that particular environment. So I'm providing that as an example of how we can achieve new levels of operational decision support for you. Now, another issue, and a very pertinent one, relates to what is the runtime reliability of field robots. And in the video at the bottom of your screen, you're seeing the Husky platform in a constrained space environment during the mission. Now, this wonderful daisy chain that you're seeing evolve in the bottom of the screen is actually us doing runtime reliability ontology. As the robot goes through different stages of its mission deployment, it uses different subsystems. And dependent on that usage, it will affect its reliability. So we've actually developed a way to devolve front-end runtime reliability and prognostics into these systems. And we can couple that with our cyber physical tools, which helps the remote human in the loop. So I won't go over that in great detail because I'm just summarizing the standing start we have. That final video on reliability ontology, you're seeing it summarized in this wee infographic here. Very pleased to have published that in partnership with ClearPath. Here's a really exciting part that I hope resonates with you all. Today, we have a symbiotic digital architecture that allows us to fully synchronize 1,000 devices and models into one environment with full bi-directional communications, therefore control and knowledge exchange. So that's the blank canvas we have to work with. Okay, that's a very powerful enabler, providing that runtime, near to real time, interactive engagement, the ability to query the resident system on an asset, on its own state of health. Now, the way that we support that human who has this, unprecedented reach now, okay, with this resident cyber physical system, is we embed these reliability ontologies within these frontline systems. We know that for that human in the loop operator, It's about actionable information. It's not about big data streams. Okay, so just to summarize, because I'm about to lead into the description of the experiment where we're inviting your engagement, okay, and perhaps against even better judgment, our demonstrator is not going to have you witness us controlling a multi-robot fleet. We're actually going to devolve control to the stakeholders. We're going to give you a dashboard where you will inform the mission scenario, the variables, and we're going to make the environment that these robots are in very dynamic. So we're going to put this cyber-physical approach to resilience to the test. So just a quick recap before I explain to you the experiment that you're getting to shape. So we are taking a top-down view to address the operational barriers to resident autonomous assistance. Okay, we have this scalable symbiotic digital architecture. We have that. Okay, we've done it for individual robots, we've done it for large infrastructure and in terms of digitalization, and now we're able to synchronize the two together. Okay, we have created runtime reliability ontologies as well as prognostic and health management analysis. Okay, now that is a key part of both the resilience and safety piece. For example, if a component becomes compromised, it doesn't mean the mission is over. It means it can adapt in many instances and remain productive, but in a slightly more limited capacity. Okay, we have in our possession just now, we've got a multi-robot team. Consider them your new colleagues. These are ground robots. We have Spot, we have Husky, we have several drones, light and slightly more robust aerial platforms, I would say. And the view that we are taking is, with that resident multi-robot team, how can we not only perform operational requirements resiliently, efficiently, productively, but can this multi-robot team help maintain itself? Could, for example, the aerial robot provide a spare component that the other robot requires? When the safety case is challenged and there's unanticipated human interaction, could some robots monitor that safety case whilst others continue with the task at hand? So, what is this experiment that I'm hoping you take this opportunity to engage with? And I'm going to let this video run. It doesn't have sound, so please don't adjust your speakers. Okay, this is me framing the context of this work. Okay, so we're aware of how offshore operations are done today. Okay, we appreciate that. We've engaged with industry stakeholders to understand, what are the operational priorities? How do you deploy people? The risk assessment, safety assessment. What tasks do you have them performing? What are some of the dynamic constraints that sit out with your control? So we want to take people away from some of the more hazardous, challenging environment deployments. Okay, so we want to look at how can we embed a multi-robot team. Could be working in constrained spaces, working subsea, working at height. So how can we address risk, safety, productivity, and general downtime? There are other emerging trends that the industrial sector will have to contend with, such as, circular economy and other sustainability KPIs. And we think these resident robots and AI architectures can really help address some of these emergent trends which are on the near horizon. So how are we going to do that? How are we going to create something representative? Okay, well, what we're going to do, and the video is going to show you this, is we have taken a well-defined use case, okay? So we are focused on asset integrity, and we're going to replicate the operational space of a facility within that offshore environment. So in the nice, warm, comfortable labs of Heriot-Watt, to help us mitigate the challenges of accessibility to offshore facility, we are going to create a really dynamic operational space where we are going to perform 2 asset integrity inspection objectives. One will be based at looking at corrosion under insulation on some ground-based assets. Another will be an aerial inspection looking at a composite. So 2 different structure types, 2 very important types to asset integrity challenges. And we're going to replicate that specific mission space in our labs so that we can actually create more variables in that space, okay? We want to be able to adjust the environmental parameters, the safety case, okay? We want to look at how do we respond to faults or queries, okay, from the human operator. And by taking a replica, okay, of that operational environment, putting it in the lab and allowing ourselves with embedded actuators and sensors to make that a bit more dynamic, okay, we will look to verify how the cyber physical system can support, as I say, resilience, reliability, safety, compliance. Now I've paused the screen here so that you can see, we have created symbiotic digital models of large petrochemical plants. We've done that. We've done it for big infrastructure where people can intuitively engage and integrate, collaborate with the information that's in situ. So we're taking that ability and we're now integrating into that space these resident robotic digital twins with this fully live and interactive symbiotic digital architecture. So synchronizing these models, getting that accurate representation of that real world need allows us to then have that connectivity to the resident operation, allow us to also do pre-planning as well, where we can take a short-term view of what can be done in that particular space. I'm just going to speed up this video a little bit. Obviously, you've no doubt seen this character well publicized by our team. So, as I say, we will build reliability ontologies that sit within these devices. Okay, so this is the multi-robot team. These are your new work colleagues. Okay, maybe not the most conversationalist at the Christmas party, but useful in the 9 till 5. Now, we will put them into this dynamic environment, okay, in an integrated, coordinated way. How can they support each other on safety case queries? How can they support their individual reliability and resilience? If, for example, Spot has an emergent failure issue or a pathway is blocked that cannot be navigated, how can we then deploy them? Okay, so I won't take you through this full animation, but it's trying to articulate to you how we will replicate that environment. We will embed the challenges you see as being the most pertinent, okay, and this is then to give you this transferable cyber physical architecture so that you can create trustworthy autonomous assistance. Okay, so that's painting the scene. Now, the dashboard that I made reference to, and no doubt could be a point of regret in the future, because obviously it makes it very challenging, but this is what we should do. We focus on the challenges, we focus on the knowledge gaps. We've defined these 4 thematic variables, okay? And we are going to work with you using what we call persona charts. I'm going to let you see what one of them looks like so that we can capture some of the operational requirements, risks, safety concerns that are vital for trustworthy assistance. Okay, so I'll let you see what one of these charts looks like. And what we would do with your feedback and engagement is we would work to how to define and create a solution to that specific challenge. But then when it comes to how do we address or the verifiability, we will randomize the variables in this use case. And as I say, once fully developed, we will hand control to you so that you can interrogate the system. Okay. So we have this field robotics lab at Heriot-Watt. We're going to instrument the infrastructure. We have decommissioned wind turbine blades and other large assets that we're going to inspect for asset integrity requirements. Okay, we've got some really interesting and novel non-destructive evaluation technologies being used as well, such as frequency modulated continuous wave radar, which allows us to do surface and subsurface scans of structures through non-contact. So that's very exciting as well. But the core focus, the primary objectives of this research is how can we mitigate the risks that are clearly there in the dynamic world. You know, if we have, for example, a person approaching a doorway, a point of entry into what is a constrained environment, how can we have foresight to understand that that risk is emerging, and how can we respond proportionately without simply stopping all operational productivity? So, persona diagrams. Okay.
David, just to jump in, we've got 2 minutes left, so if I could ask you to wrap up.
Okay, I'll wrap up. Yep. Thank you, David. So, how we capture your feedback, we're going to use these persona diagrams to map through these. There's 4 thematic scenarios. We want to capture the issues you want us to deal with, and we'll develop mitigation strategies. So, how could the symbiotic system coordinate, collaborate, and cooperate? Moving on, you've seen this dashboard, and we will make that available, as I say, to our stakeholders and participants in this experiment. In summary and in closing, and apologies for overrunning slightly, David, you know, we want to give you this cyber physical architecture. It's going to be modular and tunable to how you address resilience, reliability, and safety compliance. We will work with the personas that you help us to populate. We're actually going to devolve control to you when it comes to then engaging with and hopefully trusting in the cyber physical solution. And we see that as a great enabler to the future needs of scalable multi-robot fleets. And if you wish to see any of the information provided, there are video links to it. Thank you, David. I'll stop there.
Thank you very much, David. That was really, really good. So we've got one question in the chat that I think we've got time to address quickly. So David, at what level do you anticipate that the mission, and thus mission planning, could be described?
What level the mission planning will be described? So we will have mission planning, so that will be accessible to the human in the loop. Okay, it will also be devolved into the robotic platform as well. And the mission planning, we have the primary objective, which is the asset integrity function in this particular use case, but that will be adaptive, and it will be adaptive in the context of how we update it in the safety case and in terms of emergent reliability trends. So the mission planning will be adaptive. We will have the environment mapped out, the objectives clear, but resilience is based on adapt and survive, but ideally adapt and thrive in the future. So yeah, we look forward to mapping out the mission objectives that account for these risks with the industry partners.
Lovely, thank you, David. So at 1 minute past 10, I think we probably better wrap up there. So thank you very much, everybody, for attending today. Thank you to everybody who has attended all these sessions this week. And thank you very much, David, for your presentation this morning. Just as a quick reminder, we have David's AIM Day on Thursday, the 12th of August. So if you're interested in getting involved in that, please do drop me a note at my email. It's d.wable@hw.ac.uk, and I will take it from there about how you can get involved. Thank you very much, everybody. Enjoy the rest of your day and enjoy your weekend.